let's begin. Let's get through the rest of the examples. So last time, that's not working. Is this one working? Last time, so we saw that f of x equals x squared was continuous everywhere. Right? In fact, it was one of the polynomials, one of the 6 elementary continuous functions. So that graph, of course, looks like this. I don't have too much. Like this one. And then we looked at the other one, the f of x equals x squared minus 4 over x minus 2, and we found that that was continuous as long as we weren't 2. And we actually drew this graph, or at least drew a very similar one before, and of course the picture here was that it pretty much reduces to a straight line except at the point 2. At the point 2, I believe it was at a height of 4, and other than that, it behaved like x plus 2. And this was a gap at 4, right? So if you drew the picture, you can see, yeah, that's definitely discontinuous at 2. But otherwise, it's just like a line. That's just keep going, no break, no disruptions, no gaps. In C, which we did, we made it piecewise. So at 2 there was a problem, but we redefined it so that at 2 it actually was 0. So what you realize happened in this situation is we had a very similar kind of thing going on. And someone tried to fix the problem. There's a hole here, but they did a bad job at it. You had one job. Okay. And yeah, you messed up. You filled it in at 0 when the problem was over there at the height of 4. Now, that's still not continuous at 2. You still had a jump. You're drawing the graph, you had to lift up your pencil, go down here, fill that in, come back up here and continue. Right, so the continuity here didn't actually change, right? Continuous on, it was still minus infinity to 2, union 2 to infinity. So we actually did the calculations last time, but here's what's going on with the picture so you can actually see, oh yeah, it's not working. This one, no problem, that just keeps going. This one has a hole at 2. This one had a hole, we tried to fill it in, but we kind of messed up. In D, how do you do D? D was 4, x was 2. What did you write for D? Yeah?
It's continuous for the whole thing because there's a hole at x equals 2, but then it's filled in.
Right, so like above, if your x was not 2, we're fine. But now, at x equals 2, how do you know it actually works? How do you know it was continuous there? What did you check?
Because if you do the graph, you know that where the hole is.
Yeah, without the graph, let's, what the kind of thing we were doing.
Oh, you
Last
cancel it and then plug in the 2. Cancel the x minus 2 from the top and the bottom.
First effect.
What did you do for that?
Like simplify the function. So that
Remember,
says-
you want to think in terms of the strategy. What were the steps? I gave you 3 steps last time to go through. What was the first step? What was the first thing you checked? You wanted to check if f of 2 was defined, right? That was the first step. Is f of 2 defined? What is f of 2? Well, it's 4 by this definition. It says when x equals 2, the function outputs the value 4. So that happens by definitions. Okay, now what's the second thing you wanted to check? Yeah?
The limit of the function approaching.
Does the limit exist? So, does that guy exist? And so, now that means, if you look at this function, now at 2, we're 4, but limits don't care about being at 2. Limits care about everywhere else as you're getting close to 2. So this one is going to require you to look at the limit of the top part. And that, yes, you follow the limit strategy, that's a whole other strategy you have to apply. First thing, you try to plug in, it doesn't work. Second thing, try to simplify the plug-in. So at this point is where you come in and say, oh, you can jump to it. And now you can plug in, you would get 4. And then the third thing you check is R1 and 2 the same. And so you just look, in 1, I got the answer 4. In part 2, I also got the answer 4. Here, it's yes. And what that means is, f is continuous, not in general, it's continuous at 2. Right? It's continuous at this point that you were doing all these checks for. But we also mentioned that if you're not 2, everything was fine, because we could, pretty much the same thing that worked out in these 2 cases is going to work out over here. 2 was the only thing that potentially had a problem because we divide by 2 over here, but this time we checked it, the function was redefined at 2, and this time it turns out that it seems to actually be done right this time. Once I'm done right, you do it yourself. And here at 2, originally there was a gap, but then we came and we filled it in. And we filled it in at the level of 4. And it turns out that was actually the right place to fill it in. Now there is no gap. Now I can just keep going without lifting up my pencil. There's no break, there's no jump, there's no gap, there's no disruption. And this function, as defined piecewise here, is now continuous on the entire real line. So the example D is continuous everywhere. And that's, you can also say that phrase, continuous everywhere. So again, you'll notice here, I kept reusing the same example because I wanted to actually make a point, make that point, that even with minor tweaks, you just have to pay attention to how the function is defined, and you want to pay attention, are the points filled in all the right places? Do these 3 things exist? And you can tweak little functions, and you can fix a problem that was there. Don't really have to know about this, I don't think I'll ever ask you about it, but something like this is what's called a removable discontinuity. Meaning, here we have a function and it's discontinuous in its original state, but it's possible to fix it so that we don't have a discontinuous function just by redefining it at 1 point, or finite in many points. Some functions are discontinuous in a way that that can't work, right? So like anything where there's a jump, you couldn't do that. Right? So if your function looks like this, good luck, you can't fix it. You literally have to change an infinite number of points to fix that. But some functions have things that are called removable discontinuities. You can actually fix them. Yeah.
For a question on like a test or a quiz, if we had something like this, would you want us to like write each step on the bottom where you first did like f is continuous at x equals 2, and then write f is continuous everywhere? Or would you?
Yes, I would expect you to mention both.
Okay.
Because I want you to recognize that there's a potential problem at 2, and you are aware that elsewhere there is no problem. I want you to be aware of that. I don't want it to like you kind of guessed. And so you should, for you to be able to say this on the entire real line, you must have considered the entire real line. But 2 is considered in a special case here because this top one would divide by 0 and 2. That's why you consider it. You singled out 2 specially, but you sort of thought about it everywhere. So when you're taking these limits and finding these points here, it's for a specific point. It's for the point 2. So it works out at 2, and you know elsewhere it works out, so it works out everywhere. So yeah, I would expect these 3 points to be made in a full solution. What about E, last one? Okay, so not minus 2, and 1 at x equals minus 2. Okay, so from beginning to end, someone tell me how to do this one. So yeah, through this on the next test or the next quiz. Yeah.
So basically, I can see from just the way it's set up that there's like a potential problem at -2, if that makes sense.
Okay,
That's
so
what
you
it's
use like potential problem at -2. Okay, how would you deal with that problem?
So then what I did was I ended up just going straight to the first function and like simplifying it
Okay,
to see what -2 would be, if that makes sense. And then I saw that if I did it right, I think I did it right, it was 1. Does that
yeah,
make
so
sense?
how would you actually write it out? Tell me how you actually write it out. So potential problem at x equals minus 2, you notice that, what do you
Yes.
actually do?
So then I rewrote like top piece of the piecewise function. And like the bottom, yeah. And then I like simplified the top, or made it like 2 factors, does that make sense? X plus 2 and x plus 3. Canceled the x plus 2's. Yeah, then plugged in -2.
Why would you plug in -2?
Because I was seeing like, on that piece of the function, what it's supposed to be, if that makes sense.
Okay, but how would you express that that's the idea? Like what prompt tells you to plug in -2 here?
I was trying to see if the limit exists.
Right, so you have to write it, like you have to say that you're finding a limit. So you say you were finding the limit as x approaches -2 of f of x. Because nothing would prompt you to just randomly plug in a -2, you see what I'm saying? Like if you were to explain this to somebody and you just got to a point where a random note, like why did you do that? It's kind of surprising. Right? So you'd say you're finding the limit as x approaches -2 of f of x, which is just the limit as x approaches -2 of this, which is equal to the limit as x approaches -2 of that, which is equal to the limit as x approaches -2 of that. So you're finding the limit, so now it makes sense plugging in
Yes.
-2 is the next logical step. And you get +1, -2 plus 3. Okay? So you have that bullet point. What else would you write now?
Can I phone a friend for the next step? Because I don't know, like in my head it makes sense that like if it's supposed to be 1 and it's defined as 1 on the second piece, that it wouldn't be a whole or anything.
Okay, so like what you're saying, you need to write that. Like you're saying the right thing, but you actually need to write it out. You need to make a point. Oh, at -2, it is defined. What is it defined as?
1,
1.
which is also what the
And
limit is
then
supposed
your
to be.
third bullet point are, these are equal. So then you're going to say, so these 3 bullet points together, what information does that give you? What conclusion can you draw from those 3 things? Yeah?
F is continuous at x equals -2.
Right, it's continuous at -2 specifically. Okay, now how do we continue? Yeah,
Because the potential problem is filled, like in the graph, you can say that f is continuous on -infinity to infinity.
right, so at this point, so here you've dealt with -2 in detail because you saw there was a potential problem. So you really need to be careful. Okay, there's a potential problem at -2. Let's really check it out, make sure everything is cool, right? All right, what's the limit? Okay, cool. What's the definition of the function? All right, cool. Are they the same thing? All right, cool, so everything is fine. The potential problem is okay, crisis averted, right? So you were kind of worried about it, but you went in, you did due diligence, it's fine now, right? Now, because that was your potential problem, you just have to make a note. Otherwise, we're fine. Just, like, you don't have to prove this, but I want to know that you thought about it, right? Otherwise, we're fine. As far as I could see, the only potential problem was x equals -2. I did due diligence on that point. It all checks out, so we're fine at -2, and we're fine when we're not -2. Therefore,
Yeah.
f is continuous everywhere, would be the conclusion of the whole thing. So it's not just a matter of writing down these key phrases or even coming up with the right answer. The logical thought process, like what your mind actually went through to come up with that answer, it's actually more important. I know we all think of the answer as the important thing, and that's, I want to get the A and the answers all the time. No, you being able to reason through a problem is what matters. Because yeah, it's calculus 1. We're not doing anything crazy in calculus 1, but eventually, the assumption is, if you're like a science major, eventually you'll be tackling big problems for which there is no answer. Do you know how to think through those problems, right? You can't say, I know the answer because I can look at the back of the book. No, you don't know the answer. How do you get to it? What are the logical steps that goes from point 1 to point 2 to point 3? How do you get from a point of, I don't know what's going on, to, oh, that's the answer? It's very important. I do appreciate that it might seem annoying to you as a student to have to write all this down, and kind of knows, but it's actually important that you know how to express your thoughts logically. They go in a certain order. You don't randomly plug in something anywhere. It's very clear why you're plugging in. Everyone will know, okay, this is their thought process. This is what they're doing. This is what they're thinking. This is why this had to follow after that. Right? I want you to be able to express that. Right? So when someone writes this out, if you just randomly actually, you didn't write any of this, and you didn't write any of these limits, and you just did this calculation and got 1, and then tell them, oh, it works everywhere. It's not really logical, right? Like how do you jump from that point to that point, right? You didn't show all the minutia, which is important. It's actually important that you can show. Okay, now if someone wrote this on their paper, it's not exactly how I would have set it out, but it's perfectly fine. I would give you full credit if you wrote it out like this. Someone sees this, I can know what they're thinking. They spotted a potential problem. They dealt with that problem. They realize it's okay at the potential problem, so the potential problem was actually a fake out. They consider that other than that potential problem, everything is fine, and so we're fine everywhere. There's a logicalness to this whole thing. I can know what this person is thinking exactly, and I can know that they're thinking correctly. You know what I'm saying? It's not just like, oh, I did these simplifications, and that's the answer. You could have peeked over someone's shoulder and gotten that in 5 seconds, right? For you to actually go through this, that's what I want to see. So that would be what a filled out answer would be like. So like, I mean, on a quiz you'd get away with it because the quiz I'm only checking the actual answer, but on like a test where you're writing out your work, you'd want to set it out more like this if I were to ask you a question like this. Where is this function continuous? I expect you to see you go through the thought process. Here are the potential problems, I dealt with them. This one is fine, so it works everywhere. Or here were some potential problems, I dealt with it, and it actually doesn't work out. So it doesn't work there. It only works if it's not 3 or whatever. Right? I want to see that you're actually thinking through the problem. Because learning how to think is actually important. Unfortunately, they don't teach that in schools anymore, apparently. I think it's not in vogue anymore. So I just plug in the computer, it'll do the thinking for you. The only reason why the computer can do it for you is because human beings thought about it prior to that, wrote the computer code to solve the problem. But in the future, you're going to have problems that those human beings never thought of. Now what are you going to do? All those human beings are dead. We just have these computers that can solve old problems, but they're new problems now. Who knows how to figure out the new problems? No one, because everyone just knows how to plug into a computer. Computers aren't your own salvation. And I guess that's what AI is about. People are trying to, let's teach the computers to learn so I don't have to do anything. But at some point, you're going to need a human intervention. You're going to need someone to dream and imagine. Here's something we want to accomplish. How do we get there? How do we get from here to there? Very important. I wanted to, I don't want to mention that. I guess I'll mention that. It's actually a bit overdue. I probably should have mentioned it before I spoke about continuity, but I just wanted to actually explicitly list out the properties of limits, the things that you can actually do with them computationally, limit properties. So these are things you're allowed to manipulate. If you're ever wondering, can I actually do that? I'm going to tell you what specific things you can actually do with limits. Let C be a constant, and suppose the limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals m exist. So these guys cannot be a D and E, for example, and are finite. So not only do they exist, but they can't be infinity. So you have these limits, they're not infinity, they're not D and E, they are actual numbers that you can actually get. Then the following hold. The algebraic rules of the game. If you're taking a limit of a constant, it's just a constant. You already have to think about it, right? Limit as x approaches 7 of 3. The answer is 3. Now we actually did that before, and it was pretty easy to come up to that conclusion, but you should know that explicitly. Here's another thing that you should know explicitly. If you have a constant times a function, then this is the constant times the limit of the function. In other words, you can factor constants outside of limits, right? So you can move a constant in and out past the limit sign, and that's legal. That's something you're allowed to do. So you can compute 5 times something and find the limit, or you can find the limit of the thing and then multiply by 5 afterwards. You'll come up with the same answer all the time. It will actually always work. As long as these are numbers, right? So that's like C times whatever L is. One thing you should notice is that limits distribute across sums. So if I have two things being added together, you can actually take the limit and distribute it. Remember, not everything distributes across sums, like ours don't. So knowing when something distributes across a sum is important. So it's actually legal for you to make a move like this, and there will be situations where that's actually pretty convenient, to actually split up the limit into several smaller chunks that you can deal with. And sometimes there are even cases where the smaller chunks are hard, but when you combine them, stuff simplifies, and that's easier to actually do. But you should know that that can actually work. So with a plus or a minus, you can split up a limit. The limit will distribute across the sum. Now here's something that's quite strange. Limits will distribute across products as well. So this will be your L plus or minus n. Now if you have two functions multiplying each other and you take the limit of that thing, you can actually take the limits individually and multiply the answers together. That's allowed. I'll give you L times m. Now that's strange. It's nice, but it's actually strange. It's very rare that something will distribute across both sums and products, right? So like I was mentioning on the first day, powers don't do this, right? You can't distribute a power across a sum. It does work for a product. Limits work for both of them. It's very nice. It also can distribute across divisions. So if you have one function divided by another, you can actually take the limit of the top and divide by the limit of the bottom to get L over M, provided, of course, you're not divided by 0. Limits can pass through powers as well. So if you have a limit of something to a power, maybe the limit of something under a radical, for example, you can actually take the limit and move it inside the radical, compute the limit of the inside, and then take the radical of the answer. So this would be L raised to the n. And normally this is stated that n is greater than 0, because we don't want to worry about negative powers and going into the denominator and division by 0. But it'll work more generally still. If it's negative, you just have to apply property 5 to help you figure out what's allowed. But yeah, these are the things that you can, computationally speaking, like when working something out, you can do these things with limits. And as you can see here, limits are extremely nice things. They distribute across everything, right? Almost anything you can feel like doing with a limit, you can actually do with a limit. I can factor out, I can distribute, I can split stuff up, I can combine stuff. They're very forgiving, they're very nice. So that's something you should be aware of. With limits, you can do all that stuff. Now, for the next phase, I think we're actually going into another chapter in this one. I think it's chapter 3. Let's actually solve the rate problem. So remember, I told you, one of the goals of calculus, one of the reasons why this subject exists in the first place, is to solve the rate problem. We want to find a way to figure out how fast things are moving. What things? Anything in theory. How can you figure out how fast something is changing? This is called the rate problem. And it turns out, with limits under our belt, we now have the tools necessary to solve the rate problem in a very elegant and sophisticated way. Here's a motivating example. Suppose you have an object moving at, say, a constant speed. Right? So you're watching something that's just moving, right? Maybe you could be watching the planets going across the solar system. As far as you can tell, it's not speeding up, just going at a steady pace. And you track its distance over time. Let's say you found that the object, let's say you're tracking distance, let's say you're doing it in miles, be a little bit suggestive here, and over time you're tracking it, let's say in hours, and okay, so you start your stopwatch and you're measuring how far this thing is moving, and let's say it starts from position 0, and you're watching it, and it's moving at a steady speed, so you expect the distance to be changing like a straight line. Let's say after 3 hours you measure how far away this thing is. So as far as you can tell, it's not changing its speed, but 3 hours later, it is now 150 miles away from the original point it was at. Now I'm going to ask you a question that at first it's going to seem like it's coming out of nowhere. But it's the thing that people like Newton and Isaac Barrow noticed when doing things like these, when they're tracking things based on distance. What is slope of this graph. Right, it's a straight line, so we can find the slope. How do we find the slope? y2 minus y1 over x2 minus x1. So y2 minus y1, so it's y2 minus y1 over x2 minus x1. y2 is 150. The original was 0. x2 was 3. The original x was 0. So you get 50. Right? The slope is 50. Now, here's another follow-up question. Interpret that 50. What is that number? If you were to say, what does that 50 actually mean in this context? What do you think it means?
The rate in miles per hour.
The rate in miles per hour. How do you know it's miles per hour? Because the units on the y-axis, and of course I put the units for very suggestive reasons, the units on the y-axis are measured in miles. So this 150 isn't just a 150, it's 150 miles. 0 miles. This 3 is in hours. That's 0 hours. Right? So this here is miles divided by hours, right? Or miles per hour, right? So this is the 50 miles per hour is the interpretation. In other words, it's how fast the object is moving. Right? Something's moving at a constant speed. If you track its distance, you'll get a straight line. The slope of that line will always be how fast the object is moving. In other words, at least in this case, there's a connection between slope and speed. Or another word to say that, rate of change. So in a very simple case, this case, where something is just moving, but it's not really changing how it's moving, it turns out that if you were to track its distance, the slope of that graph would actually give you how fast the thing is moving. And pretty much this is how all mathematical ideas begin. You start with a situation where you can pretty much understand that situation, but it's a very basic situation, hardly applies to anything. What moves and never changes how it moves? Nothing, right? But understanding this basic situation, now what you try to do is you want to try to generalize this. Can I somehow apply this idea to other things? What if it's speeding up and slowing down? Can I still do this idea? Can I still figure out how fast it's moving by looking at a slope? What would slope even mean in that case? I know what slope is for a straight line. Is there a generalized version of a slope? So that is another follow-up question. So we notice that in this very simple example, finding slope is equivalent to finding speed. The follow-up question is, can we generalize this? And the answer to that, surprisingly, is no. So I guess we're done here. I'm kidding. Of course the answer is yes, because that's what calculus is about. Calculus figured out a way to do this in general. How do we generalize this idea, right? What if we were drawing the graph and it was wavy like that? Could we still measure a slope somehow? Could we still talk about rate of change? The answer is actually yes. And here's how we do it. So here's the idea. You're going to start with the average rate of change, which we defined 2 or 3 classes ago. Average rate of change. So let's say you had a graph, but it wasn't a straight line. It was just doing its thing. It's very curvy, right? Just for that. Now, what does it mean to take the slope of such a graph? I don't know what it means. I only know what it means to take the slope of a straight line. So let's say I have a line connecting 2 points on this graph, and remember we call that a secant line. I can talk how on average, its average rate of change, if this were in miles per hour, the slope of this, if this were in miles and that was in hours, the slope of this line would also be miles per hour. So this, you can think of the slope of that line as the average speed. It's the average, how fast is it moving on average. Now it's not specifically how fast it's moving, but it's how fast it's moving on average. And we can start to actually make this a little bit more precise. We can say, if I call this f of x, that's the function. And let's say this is x. And again, I'm using very suggestive notation here because I want to build up to something familiar. So we start measuring at a position x, and we continue measuring until we have a distance h away, or h time units away. The position at this part is going to be f of x. The position at this part is going to be f of x plus h. And so what you would get is that, let's continue over here. What we would get is that the average rate of change is just going to be f of x plus h minus f of x over h. I already derived that for you before. That's the difference quotient. That's where it came from. Now, here's the question. Can we do this at every instant? So if someone were to point, okay, I know how fast I'm moving on average, but that's not the point. We can do that. I want to know how fast this thing is moving at any given time, right? At that point specifically, how fast is it going now, right? Well, in the beginning we don't really know, but we can actually figure it out. So the answer to that is yes, and here's the idea. We only know how to find the slope of a line. The slope is going to be, for us, synonymous with how fast it's moving. But we don't want to find the slope of this line because that line is just telling us how it's changing on average. If I want to find out what is the slope at an instant, if that even makes any sense, I need to somehow find a way to find the slope at one point where that kind of doesn't really make any sense because we're used to finding slope using 2 points. But here's the idea. We can move the 2 points close together. What you kind of do is just cut down the distance over which, or the time interval over which you're measuring these distances. Let's not measure it over this huge distance. Let's cut down the average that we're measuring. And let's kind of close this window so that we don't have this line extending out to some average thing. It's actually much tighter, right, is the point, right? And so what we can do here is, we care about this point. We care about how fast we're moving here. So at the point x, let's say, what we want to do is we want to be able to move this point closer to x, and move it closer to x, and move closer and closer and closer. And what you're going to realize is that this line that once measured the average, now it starts to change. It starts to be a line that's moving somewhere, right? Eventually, that line is going to turn into a line that looks like this. It's going to be a line that is essentially going through a single point, right? So I move from a line that's moving through 2 points to a line that's going through a single point, right? these lines all converge to this red line, and that red line is actually the guy I care about. How can I find the slope of that line? And the question is, how can I mathematically move these points together? Well, I want you to notice what we're doing. We are closing the distance between these 2 points. But what is that distance? The distance is h. Now, I'm doing a lot of hand waving here because I'm never going to ask you to explain this, but I want you to see where the ideas are coming from. So, we don't want it over this large window. We want it over a much tighter window. So the idea is take this point and move it close to that point. That's equivalent to taking this distance here and closing that window closer. Now, if only there was a way for us to make this distance inch closer and move closer towards something. That's what a limit's about, right? The limit is going to allow us to push. That thing that we want to push, we want this distance to get smaller. In fact, we want, can't write, h to get closer to 0. I want this distance here to be almost nothing. So that drawing the line through 2 points is like drawing a line through 1 point. And that's where the idea of limits came into play. So we knew this is what we wanted to do, but we didn't really have a mathematical tool to do it. So we took a tangent, we went off on a tangent, pardon the pun, invented the concept of limits, and then we came back here to solve this particular problem. The whole reason why we cared about limits in the first place was to solve this problem. Okay? So we use limits to actually close this distance. And so now, the slope of the red line, we can actually compute it by starting out looking at the slope of the secant line, as it's called, and then just letting the distance get closer to 0. Now the slope of the red line, as you might recall, that's called your tangent line. In other words, we can say the slope of the tangent line at x is equal to this limit. And that's the beginning of some great things that we'll continue next quarter. It turns out that that's actually the key to solving the rate problem. That limit, it's a very important limit. And we're going to actually use it next time. And I'm going to give you a nice name, because you don't want to have to write this out every time. I'm going to give you a nice name to call this guy, and have some nice notations. But we'll do that on Friday. Do a bunch of examples. So we'll stop there for now. We've made a lot of headway in solving the rate problem.